Give me 2 seconds. Wait. Okay, it's live. Yeah. Yes, I do. Okay, slideshow mode is activated. Okay, so this is a test of the microphone. If you guys can't hear us that well, let us know in the chat so we can bump up the volume. It's on YouTube. And Philip says that he can hear me well, so that's really good. That means that we are live. Great.
Lawyer, languages, I don't know about
Okay, everyone. Hello there. So we're starting this event. Thank you so much for coming. I'm gonna sit down and talk to you from this kind of station that we've built here. Yeah, this is a very chill event. It's a GDG trial, as I've said. So, yeah, I guess we should start. What is a GDG? So, first of all, what is this event? What is a GDG? Why are we all here? So, a GDG is a Google Developer Group. A Google Developer Group is a community of people who get together and talk about things. It's not a very formal event. It's a very kind of casual thing. And the idea behind the GDG is to have a place where people, like-minded people who have similar interests, get together and talk and discuss ideas. So there was not a Google Developer Group in Cambridge before I came here to do my PhD. I was a part of a Google Developer Group for a very long time, so I decided to make one. And this is our trial event. So I guess the top question is, what is a GDG? And as I said already, it's a group of people who share similar interests. They gather together and discuss things. So this whole event currently is organized by me and Javier, who's at the back. But in the future, hopefully, this group will be under the patronage of Google. And what does that mean? This is the trial event. Once it's done, all of this will be submitted to Google, and then from there, if they approve, we get it as a proper Google Developer Group that we can use for Google for marketing purposes. Oh, sorry, there was a problem with the stream. So we can use information from Google. So what does that mean? That basically means that we get access to some Google tech that's in development, so we can see more interesting things that are not out public. And essentially, we also get access to Google staff, which is really good. So in this talk, we have a bunch of people that are experts in their field from the University of Cambridge. However, in the future, we can get experts in any field who work at Google or somehow associated with Google. So that's kind of what Google's involvement in this group is. A really good thing about this as well is that not only do we get experts, but we get some funding from Google, so we can, organize really cool events. We can hire different venues, order food, and all those things. So the main idea of a Google Developer Group is that it's a place to grow ideas and develop oneself. There are several sections that a Google Developer Group has and several type of events that it speaks about. And today you'll kind of get a taster of all three. So I'll keep going in a second. However, I am aware that this thing is everything is streamed online, by the way. There's a little problem with the stream, so bear with me while I fix it. So this is the Google Developer Group. Here, now, all of us have access to some food and we have access to drinks. This is all thanks to Flower. So Flower is the company who's sponsoring us today, and we're going to do a little technical showcase of... Yes, Nick? Music. I improved the music.
Oh yeah, delay. Oh, okay. If you removed it, it's fine. You didn't need to drop.
No, that's actually okay.
Yeah, the music is annoying. It's gonna go away.
I hope it does.
It's the live music.
Yeah. So thanks to Flower, we're able to afford basically to be here now. And these are the links of Flower. So Flower, just to kind of let you know, is a federated learning framework, and we'll be looking at ways today that one can use federated learning to improve privacy in machine learning, right? So Flower is a framework written in Python that allows you to federalize any machine learning model. And it's probably the easiest one to use on the market. So here I've added a few links to their social media, their GitHub, and their web page, and I encourage all of you to scan the QR codes and check them out. They're really good guys. So In the meantime, while you do that, I'll just check on the YouTube stream, fix it, and then we can keep going. Cool. Okay. Perfect. So that is what a Google Developer Group is, and what and our sponsor today, which is Flower. So what the Google Developer Groups do in general? Well, according to Google themselves, there's kind of three main things that Google Developer Groups are supposed to do. And here we can connect with local developers and technologists, we can learn about new technology, and we grow. So we apply our knowledge and connect to build great ideas and great projects. For us to support that, we invite people, as I said, to give us insight into new tech, hold tutorials, show different techniques and technologies, and basically all of us kind of, try out different things, talk about different things, and it's just a cool place where we can talk and, have workshops. So what's going on today, specifically? Today it's going to be a Google Developer Extravaganza. So what does that mean? Well, a Google Developer Extravaganza is going to show you all of the aspects of a Google Developer Group in one event. So usually there's several different types of events that happen. One of them is kind of a tech lecture where an expert from the field comes and talks about a new type of technology. Some of them are oriented towards impactful things that are really affecting people who work in tech. And the last kind of thing that Google Developer Groups do is they show tutorials. So there's training sessions on how you can, develop a server or do some front-end development. In our case, we'll be focusing on machine learning frameworks. So today we'll do exactly this. First, we'll have a talk about a new technology. Then we'll have a talk about some policy implications. And finally, there's going to be a little tech demonstration showing some of the new Google tech that's available. So that's basically it. Do you guys have any questions? No? Cool. So I'm aware that there's people online and there's a little delay on the stream. And I'll see if there's any questions online, but I'll answer those actually in our next intermission. So let's begin with the event itself. So I would like to invite here with me Professor Nicholas Lane, who is the co-founder of Flower, an expert in the field with a lot of experience. And he's going to come and talk to us today about federated learning and Flower. So please give a round of applause for Professor Lane. Hello, Nick.
Hi everyone. This is a slightly unusual sort of arrangement, but we're sitting here at a desk and looking at a bunch of people in the room. And also, I guess through this camera here, there's a few people there as well.
Yeah, there are a few people online, people here. So that's the arrangement for today.
Yeah.
Cool.
So I think the aim of this section is to discuss what federated learning is and also try to excite people about it in general. So really just trying to kind of give a bit of a background that would then allow people to understand and appreciate the stuff that comes next. So I don't expect this to be too long, but just trying to get everyone excited and on the same page. So I suppose if I just advance the slides.
Yeah, you can go for here.
And so this is the slides they gave you?
Yeah.
Okay, great. Okay, now I understand. Oh, so I think we're going to do this for like 15 minutes. Oh, is this still the right version? Anyway, so let's start with the basics. This is the kind of the world that we live in right now in terms of machine learning, and it's a centralized machine learning kind of situation here. We have on the left-hand side, we have the apps. Doesn't matter if you're kind of browsing the web these days, if you're playing with cell phones, if you've been sitting down and watching Netflix, you're interacting with hundreds of models, if not thousands of models, that have all been trained in the same way, and they're trained in the way that's shown on the right-hand side here. It's everything sort of lives inside a data center, virtually everything. Large amounts of data have to be copied into these data centers, and they're run over with centralized algorithms to train these models, and then most of the inference also happens in these data centers. So this is the world it is today. But today we're talking about a completely different type of paradigm, that of federated learning, and it looks quite different. Here is here is an animation of what federated learning is about, and essentially it turns that picture on its head, in that rather than the data having to be copied into this data center and then compute happening on it, we leave the data where it is. And that's what's being illustrated here on the right-hand side. In this picture, you see data existing on phones, but you could replace the notion of phones with hospitals. You could replace it with laptops in a corporation. You could replace it with IoT devices with nice sensors. So wherever data is naturally arising, we're going to leave it where it is. And then we're going to start to learn from that data at that location. So at each of those, in this case, phones, you're going to do computation, extract information from it, and then we have, in some sense, small pieces of the larger model we want to learn at each location. So that's stage one of federated learning. Stage two is that you need to aggregate these individual pieces together. Now, because this learning has happened in isolation of each other and without the ability to look at the data that's present on the other locations, other challenges arise from constructing that model, especially constructing a model that would be equivalent from centralized learning. But there's also a huge number of benefits from allowing the data to just sit where it is. There's obviously potential benefits to privacy, because fundamentally the data hasn't left its location. Although to protect privacy, there's other additional things you need to be aware of, because this transmission of intermediate learned information can also leak data as well. But at least you're starting with a very good sort of step. Second, in certain situations that are very difficult for centralized learning to sort of cope with, such as when you have streaming data to deal with. Imagine if you have 1 million Tesla cars around the world, you want to build a self-driving car model. One way in centralized version of events is to copy all of that data to one place and learn a model. Instead, under federated learning, other forms of decentralized learning, you could imagine learning what's the important piece of information from the data that exists in each of these cars, and then building a model through some sort of aggregation process. And so I mainly just wanted to kind of show you this is the kind of setting that we're talking about all of in today. If we go back, let's look at a few examples, because federated learning is interesting in that it hasn't taken off to be a dominant paradigm of machine learning yet, but yet simultaneously we can point to many examples of where it's being used even today. And so if you use an Android phone today, that keyboard, the next word prediction and all the sort of spell checking, all that nice stuff that you might have benefited from, is based on a model that was trained with federated learning. And so literally today, there are billions of people using federated learning, hundreds of millions of people using federated learning as we speak. There's also a lot of other sort of not nearly as well deployed examples of it. So in a lot of the healthcare scenarios for machine learning, the way that people want to move forward in those is by maximizing the types of protections you can provide to patients, and often the types of systems they want to construct would have some sort of flavor of federated learning, where the data can sit inside the hospital and not move, and you could have perhaps better cooperation between organizations that might have different types of sensitive data to help integrate the information they have. There's also a lot of promise in areas such as robotics, where you're dealing with a very complex situation, a very sort of fast-moving, things are changeable in their environment, and how you build a model that can cope with that complexity and change isn't really amenable to the situation of having a static data set that is copied into a data center and you train once. So if you can imagine, as I mentioned with the Tesla example, that type of setting is something that is much more easily realized with federated learning in this case. Let's see. So often people start with privacy, but I want to highlight a couple of examples of why I think not only is federated learning useful for maintaining private systems, but is actually fundamentally important for the future of AI. And so 2 reasons I'll point out. One is that today people are pretty excited about the amount of data we're training on. They say, oh, we're training on huge amounts of data, it's great. But they only really can say that from the point of view of the size of data we're used to training in machine learning. So the data that we're training on right now is big only in the sense of the size of data we used to train on in the past. It is not big in the sense of all the data that exists in the real world. And so this illustration here is showing you the typical data sets that are trained on by machine learning systems, even of the biggest kinds. So if you're training like an LLM, they apparently consume a lot of data, but it's only the data that's available on the internet and easily accessible via the web and can be scraped. In fact, if you stop to think, there's a lot more data out there. And I would argue that the amount of data that is not on the internet, that's not easily networked, that's not found on websites, is actually dwarfs that. And so we're talking about data that's in people's phones, data that happens to be sitting on your laptop, data that happens to be sitting on different silos out there, organizations, IoT devices, data that sits inside machines that that build other objects and so on in industrial settings. All the data that people might have that they're kind of uncomfortable in sharing and copying to a data center. There's there's sort of a very long list of data that's obviously not on the internet in the same way that can be scraped out. And then what federated learning promises, if we can solve some technical challenges, is the ability to access and use all of that remaining data. And so that data is not just about, that data shapes the applications we can build, and it also shapes, as we increasingly find out, the strength and quality of those models. And so if we can unlock that currently locked away data, then, and I believe the only way we can do that is through these decentralized and federated style learning methods, that is an important gateway to us being able to improve AI just generally. The second thing that is interesting to consider is that right now, there's a lack of compute for training these models. And what's fascinating about this problem is that most of the compute that's out there in the world can't be used for machine learning. We actually, there's a tiny sliver of compute that we say, oh, that's good to go, we're going to use it. And that is in data centers inside GPUs. But similar to the data situation, think about how much computation is actually on the planet today and where it is. It is in, GPUs under a desk. It's under, robots. It's in a car. It's in a laptop. It's in, basically, we want to use NPUs and GPUs to train models, and you just think of these big classes of like CPUs, microcontrollers. If you actually could add up all the operations in the world of computation that currently have been deployed, and if you said how much of those computations can be applied to machine learning, it would be a frighteningly small amount. And that is a failure. That is the problem of centralized training. Federated learning, decentralized learning, promises the ability to use all of that compute that's currently unused. And if you consider for a moment to think that we're currently lacking in compute, people are starved of compute, there's words like GPU poor being thrown around. If we can move to a learning paradigm that can get to that data, then that not only is about privacy, but it's also about participation. It's about advancing the technology and making sure it can continue to train large models. It's fundamental to the whole thing working. And so these numbers here, for just for illustrative purposes, this is the number of exaflops that you'll find in a GPU data center that's extremely big. It costs you about $800 million to get 22,000 H100s. So you could say, oh, big, it's a big GPU data center. That sounds pretty cool. Well, as as a reference point to build on what I've been saying, let's look at how many exaflops would exist on a class of compute that doesn't currently get used at all for machine learning. And so let me show you this one, 70 exaflops. So where could you find 70 exaflops? That seems like a crazy number. Well, you can find 70 exaflops in just simply 20 million Snapdragon Gen 8 smartphones. And so this is the number of smartphones of a particular class. I guess it was the S23 that Samsung sold in one year, about 2 years ago. So then again, I was talking about how much computers are around in the world. You can start to think of that as 1 year's sales of one class of device from one manufacturer. Then you can look at 70 versus 3. Then you get a sense of how ridiculous the current situation is. And the limitation here, importantly, is not fundamental. It is actually just algorithms and software. And so that's the opportunity. I think we're going a little bit long.
I think that's perfectly fine, but yeah, please keep going.
Okay. Where are we with this? Okay, so let me just say a couple more points. One is, as I mentioned before, the interesting situation we are today and what we're trying to change, what groups like this are trying to change, is shifting federated learning from being an exciting thing that's done in very niche applications like the Android phone. Seems really cool, seems really sexy. Problem is, every single AI system you can think of, let's start with AlexNet, let's start with, let's see, what's another one, VGG, let's think about AlphaStar, let's think about, you name it. You can't tell me an AI system name out there, literally, that was trained with federated learning. They're all trained with centralized learning methods. And so we need to change that to benefit from this data opportunity and compute opportunity, because that's where we are right now. So why is that? That's because there's massive series of hurdles of using these techniques. They're not easy to use. And any academic like myself would love to tell you about all the problems that exist in doing so. And so that freak you out with issues to do with comms and local compute overhead, that scare you with things to do with non-ID challenges and so on. And there's a large list of fairly technical problems. But the interesting thing is that when you look into it, there's been a huge amount of energy and interest and effort put into solving what I believe to be the same level of complex challenges on the centralized side, and that's been working for 12 years. And there's been frighteningly little amount of energy onto these same problems that exist. And so right now we live in a world where people think that there's inherent difficulties in using these decentralized methods, whereas I believe that most of these things can shift enormously if we just lean into them a little bit harder. And it's particularly if we lean into them proportional to the opportunity. The biggest opportunity is, and the biggest hurdle, I believe, right now to this moving forward at a much faster rate is not all these things that people want to freak you out about, why they are difficult challenges, but it's actually this one here, oh man, which is this one here, the overly complex and limited tooling is available. Right now, I can just grab some random person on the street and they can train an LLM using 1,000 GPUs with barely any knowledge of what's going on. And why is that? That's because the software infrastructure, tutorials, the code, the amount of money that someone can make out of doing that type of thing is enormous. And so we live in a world today that looks like this. You can train on 1,000 GPUs with any random idiot. And if you cannot yet do the same thing with 1,000 different devices, 1,000 different silos. But again, the flower hypothesis is that there's no fundamental difference in the level of complexity in those challenges that remain to be addressed in federated learning than has been already solved in the world of centralized. And so all we need to do is lean into it, proportional to the opportunity, and this thing will crack. So what are we doing? We're building Flower. The whole idea of Flower is to build software tooling that makes it as easy to train on 1,000, 10,000, 100,000, I don't care, number of data sources as easily as you do on centralized today. And we're already having like a huge amount of success in allowing this to be possible, mainly thanks to a vibrant open source community. Because what we need to do is have a larger number of eyeballs look at the problem, and through that sort of size, you'll start to be able to make progress on those sort of challenges. And so I'm really happy to be involved with Flower that seeks to basically be the PyTorch of federated learning. And so there's 1,200 contributors, there's 120 contributors out there, there's 1,200 really great important projects that are built on top of Flower, a lot of different things of this kind. But this is the way we're moving forward, I think. We should probably wrap it up, right?
Up to you, yeah.
Let me just see. Yeah, let's wrap it up there because I think we might be going over time. So happy to take any questions, or we can move on to the next speaker.
No worries. Well, thank you very much, Nick. A big round of applause for Nick. So, any questions from the room? Yes, please.
I find the S23 example really interesting because that really puts it into scale, like where the processing power is in consumer devices. But presumably you need quite a bit of energy to do this sort of work. Like how do you rationalize that for smartphones? Is this something that might run overnight on consumer devices while it's charging, or like how do you think about it?
The way I think about it is just unused compute. And so then phones are an interesting opportunity, but it's not the only opportunity. So I wouldn't want to sort of obsess about that one because it comes with a few issues, right? So it's like, who owns the phone? When are you going to plug it in? What sort of connectivity it is, and so forth. I think the important thing is to be able to have machine learning workloads leverage all the different computers out there. So it can be laptops, in an enterprise where the data happens to be, and then there's no point in having situations where you say I must ship the data somewhere before I can start training. It makes I think it's better to have situations where you can just use even a small amount of compute to start to extract some information, some learning from where it happens to be, even if you don't go very far in the situation. And that does wonders for reducing the amount of compute that you eventually have to do somewhere else before you get a useful model. So yeah, but the phone thing, I think, it's just waiting for the right company to come along to realize that probably the next big monetization opportunity of a phone, after you've done all this sort of, advertising and you've got paid this one-time cost of getting the device, is probably turning that thing into just processing user data in a safe way.
Ooh. Another question over there. Yes, please.
Yes, thank you for the great talk. I was going to ask, do you perceive a future where people are going to be renting their own computers for processing, like when they're not using it?
Possibly. I think there are lots of different types of models of usage that could arise. So you could have situations where people want to sort of rent, and it's very explicit about some sort of like exchange of value to use the compute. But I rather think of situations where we build systems that the way the system works is that some of the learning happens where the data is, and that happens to be a much more, it creates a model that's just so much better that's the way that we want to build our AI systems. And so it's not a question of incentivizing a doctor to put data in, it's a question of like, oh, well, I'm going to build a more decentralized system because it's private, it's safer. Not only that, it uses more data, so it's fundamentally just better. And I can never, what I think will eventually happen is we'll realize that all this idea of actually shifting data into a data center is only good for toy problems, because actually the real data is out in the world. And so if you really care about non-toy problems and non-toy data, you have to build systems that are decentralized. So I think that is the end point.
To ask a follow-up.
Yeah.
There's a lot of data on internet, but for the language models, for example, they also like filter the data with quality filtering to make sure that the data they're training is something that they want their models to learn in the first place.
Yep.
Like those type of challenges, would you suggest any paper on those type of challenges? Is that something that's addressed?
On data quality challenges?
Like if you don't know which data that you're training in, like on the computer.
Yeah.
Yeah.
Oh, is there a question about its problem of data quality in general, or in the context of federated?
When training on local data that is protected because of like privacy constraints.
How do you bridge that gap?
Yes.
I think there's frightening little work done on that yet. So it's like a necessary piece. But yes, we have to think of, I think there's one thing academics are failing at is stressing so much about this issue of optimization. How do you do it when the things are independent? And then just like important problems to do with the complete chain of building models. How do we make all of those steps decentralized? And so one of the ones that you're highlighting, if we live in a world where you can't reasonably look at all the data, or it's just you can't copy the data over to look at it anymore, because that's what a data scientist often has to do in many cases. If you can't do that, then what's our solution? And so like automated data quality is an important thing, but also just like ways of interrogating data to understand if the model's using something useful, but doing it in a way that doesn't mean that I have to look directly at the data. Maybe you can have sort of intermediate results or intermediate calculations, all of that stuff. I haven't seen much work. I'm sure there's a little bit out there, but I haven't seen much.
Thank you.
Great. Any other questions? Okay, well, thank you so much, Nick, for talking to us about Flower. Yes. Great. Well, everyone, so this was the first tech talk of the Google Developer Group in Cambridge. So a very, very impactful moment. Now we're going to go and talk less about tech and more about things that affect tech, affect our research and affect, machine learning in general. So I would like to invite Bill Marino over here to tell us about this. Round of applause for Bill. So Bill has a law degree from Columbia, am I right?
That's true, yes.
And you have a master's degree in computer science from Brown University.
I have one from Cornell and from Brown.
Oh, so you have, okay, two of those. Additionally, Bill, I know that you have a course in Cornell Tech.
I teach a course at Cornell Tech, which is the name of Cornell's campus in New York City. It's called Productizing Machine Learning.
Okay, and I've also heard that you are going to give the same course here in Cambridge.
The rumor is true. I
The
can
rumor is
confirm,
true.
yes. I will be giving an abbreviated version of the course next week. It counts as RSP credit. That's next Thursday. And I'll show the information on the board a little bit later.
Great. Do you want to give us a brief kind of overview of what that course is going to include? Or?
Yeah, course is about turning AI and ML technologies into great products and businesses, walking them through the product journey. So yeah, it should be pretty fun. Please come out if you can. Next Thursday, 2 p.m.
That sounds great, Bill. Well, today we're talking about
Should we go to screen slideshow? There we go.
absolutely.
And this is what I use right here.
This is what you use right there. So today you'll put your lawyer hat on and talk to us about the EU AI Act. So before we begin, can you just tell us kind of quickly, why does this matter, just before we start with the act?
Yeah, I think, you know, the purpose of this talk is to kind of break it down a little bit, tell you why it matters, give you some practical tips. But at a high level, I think this is about to become not just the EU AI Act, but AI regulation. It's going to become one of your big blockers whenever you're trying to ship something in the real world. We'll talk about the fact that the EU AI Act has a big research exception, so it might not affect what you do here at Cambridge, but anytime you're handing research off to industry, or if you're out there working in industry, and there's a couple people here that are actually from industry, not from Cambridge, right? And hands in the air, who is from industry in the room? Okay, thanks for coming out. So, you know, this could start affecting you this year or next year in a major way. So I like to say it's going to become one of the big blockers for every ML project out there.
Great. Thank you so much for this brief kind of introduction to the topic. And yeah, take it away.
Thank you. Did you want to open the doors, by the way?
I think it's fine for now. Okay, guys, just for everyone who's in the room, do you think it's warm or do you think it's cool in here?
Who says two? Who says
Who
two?
says cool? No one says cool. Who says warm? No one says warm.
It seems good.
Okay,
Okay.
cool. Well, we'll continue on. Okay, Bill. So take it away.
Thank you. So, you know, unfortunately, EU AI Act, it's a little bit of a, let's be honest, a little bit of a boring topic, right? And what's worse is that you're going to find that my slides are probably even more boring. Psych, I had these sweet 90s theme slides to keep this exciting. I think this is going to be a pretty radical experience for everybody. So this is the EU AI Act, which again is sort of at the vanguard of AI regulation. And we'll just, you know, we're going to break this down and tell you what you as researchers or developers need to know, okay? We're going to keep this loose. If you want to chime in with questions at any time, please do so. Cut me off when I've gone too far. I'll cover as much as I can cover.
Absolutely.
Okay, so disclaimer, I'm actually a retired lawyer. I've officially retired as a lawyer. Began my career in law, but then switched into computer science. So this isn't legal advice. I'm also pretty new to EU law. So there might be folks in the audience that know it a little bit better than me, or certainly the legislative process. So chime in if I say anything that's off, or if you want to add anything. I'm skipping certain parts of the act for brevity. So was someone about to say something? Okay. So this isn't legal advice. If you're actually putting things on the market in the EU, and that's kind of the threshold, then you should maybe think about getting yourself some real legal advice. So too long didn't read. If you don't remember anything that I say, just remember this. There is a big exception in the EU AI Act for non-commercial activities like research. So a lot of what you do here at Cambridge is going to be accepted out of the act. But, you know, sometimes there's a fine line, right? And as I said, a lot of you will be headed into industry or maybe working with industry partners. And the flip side of that big exception is that there are big penalties if you get this wrong. Up to 35 million euros or 7% of global revenue, which if you're a startup could be crushing, right? So it's definitely worth paying attention to this stuff if you wind up putting things on the market. So who and what is covered by the EU AI Act? I'm going to kind of distill this down a little bit. There's different roles, and they have different rules that they need to comply with. But the big one that I think everyone here should know is that this covers providers of AI, which is really a way of saying developers, who place AI systems or general purpose AI models, and we're going to talk a little bit about what both of those things mean, on the EU market, okay? So really putting them on the market, selling them in the EU, regardless of where you as a provider are located, right? So if you're, US based, but you're putting stuff in the EU market, is going to apply to you. As I said, there is a big exception for non-commercial use, like research. There is a partial exception for open source, and we'll talk a little bit about that later. So if this applies to you, what rules apply to you? Well, there's two important paradigms here, and one really goes back to the beginning of this legislative process, and that's what's called an AI system. It's pretty intuitive, I'm not going to spend much time defining it, but if you think it's an AI system, it probably is. So include any of the machine learning stuff that you're doing, for example. Within this paradigm, there's two sort of big buckets that you really want to know about, and they have separate rules. The first is prohibited AI systems. So there's a class of AI systems that you might be building that are just going to be prohibited going forward in the EU. We're going to talk about what these are. You just cannot do them. That's what you have to remember. Starting probably later this year, actually. This is one of the first things coming. There's also high-risk AI systems, okay? So these are maybe a little bit less risky than the prohibited group, but they still bear some heavy risk. And so these are going to be pretty heavily regulated. And I'm going to tell you exactly what these are. And then we're going to do a deep dive on some of the rules around these ones, because you could say that the bulk of the act is spent describing the rules around high-risk AI systems. But after they started this legislative process back in 2019, I think it was, the world changed with foundational models. And I think everyone realized that you could take a foundational model that wasn't, maybe on its face risky, but you could downstream apply it to risky use cases, right? So I think there was kind of a recalibration effort last year, and they wound up coming out with a new set of rules that are really just geared at foundational models. For reasons I don't understand, they call foundational models general purpose AI. I'm going to call it GPAI for the purposes of this talk. Baseline GPAI is probably the least regulated category. I'll tell you why. It's mostly just about documentation. There's a slightly riskier bucket within this paradigm called general purpose AI with systematic risk. I'll tell you what defines this. Just know that this particular bucket is a little bit more regulated, but still less regulated than the high-risk AI systems. So let's just talk quickly about this category of stuff that's totally prohibited. Prohibited AI systems, anything manipulative or deceptive, anything that exploits vulnerable groups based on age or other things like that. Biometric inferral of sensitive attributes, so inferring ethnicity or race via biometrics, social scoring, criminal profiling, crime prediction based on personal traits, facial recognition via open scraping of the web, inferring emotions at work or in school, real-time biometric ID in public places. These are all prohibited, starting probably later this year. And so what's in this next category of risk down, high-risk AI systems? I'm kind of distilling this a little bit, but here's some sort of categories to memorize, because these are pretty much, going to fall into high-risk AI systems if you're working on them. Anything with biometrics, critical infrastructure, education, employment, access to essential services, whether those are public or private, anything with law enforcement, anything with immigration, anything having to do with the administration of justice or with the democratic process, voting systems and things like that. These are probably going to fall into your high-risk system category. And again, this stuff is pretty heavily regulated. What does that mean when I say it's heavily regulated? What are some of the rules? I'm really distilling this down. There's a lot of stuff I'm not going to cover, but here's just a couple of things you got to start worrying about if you're working on this stuff. you need to have a risk management system in place. I think I have a later slide that describes what this is, but you're going to hear there's a lot of system overhead. You know, no, these are not computer systems, by the way. These are administrative systems. And one is making sure that your AI development processes are part of a larger risk management system. There's a lot of stuff to be done on data and data governance. We're going to do a little bit of a deep dive on that. A lot of technical documentation that you have to start generating and being able to hand over both to authorities if they ask for it, as well as your partners, for example, the downstream deployers of your models. A lot of record keeping, specific, logs basically that you're gonna have to start generating. Provision of info to deployers, that's again like documentation that you're gonna hand to your partners. Human oversight of AI, that's gonna be a new one for a lot of people, and we'll talk a little bit more about that, but there's basically a requirement for human oversight of AI systems. There's a lot of requirements around the accuracy, robustness, and cybersecurity of systems. We'll talk a little bit about that. And then another system is a quality management system for your data and your model. Oh, on top of all this, you have to register your system in a database of systems so that benevolent bureaucrat can just keep track of what you're doing, right? So what does this mean for the people in this room? I'm going to try to break this down in a practical way and talk about some of the things that you might start to need if you're working in this high risk category, okay? Any questions so far? So one reoccurring theme that you might have noticed, just a lot of transparency efforts, creation of documentation, creation of logs. These are going to describe all aspects of your overall process, like, what was the intended purpose? What were the major decisions that you made around your AI? For example, what users are you targeting? Documenting your training data, documenting your training process, your evaluation, not just performance, but also red teaming for risks, your inputs and your outputs, your hardware and software dependencies, documenting the human oversight features that you want to accompany your AI. So you're gonna have to start generating a lot of documentation around this stuff. As I said, you're also gonna be generating logs. An important part of here is post-market monitoring. So when this stuff actually goes out there in the wild, creating logs that describe, inference and how users are reacting to inference and things like that. A lot of new management overhead. So this is not engineering work, but you're all gonna probably have to start worrying about it. At least 3 different kinds of systems that you may not have at all today. I think if you interviewed a lot of startups, for example, they would say that they just don't have these in place at all today. A risk management system, and that involves, risk management roles, policy documents, creating processes, tracking things as they move through. This might be a risk management system that covers things beyond AI, or it might just cover AI, but you need to have it in place. Quality management system for your training data, for your models, again, roles, policies, processes, tracking of projects as they flow through the life cycle. Data governance and management. I probably couldn't have told you a couple months ago before I started looking at this stuff very carefully what data governance really was. But it's about creating policies around your data, what you can use, what you can't use, the quality levels, the metrics that you need to see in it. So again, creating data governance roles at your company, data governance policies, processes. So there's a lot of work here. Let's talk a little bit about data. So we talked about data governance, that's a requirement. Data documentation, that's a requirement. This last one's really important though. There are actually requirements around the quality of your data. It has to be relevant. It has to be representative. It has to contain, I have minimal errors here. I think the exact language is, to the best extent possible free of errors. So there is a standard setting process that's already kicked off. And I don't remember the name of the standard setting entity in the EU, but they will hopefully break something down, like break a requirement like this down, so we can understand exactly what percentage of errors is acceptable, right? But until that happens, it is a little bit ambiguous. Data also has to be complete in light of its intended use. I would also say that one's really ambiguous. So hopefully as these standards come out, we'll start to get a little bit more clarity into what the exact rules and expectations are, but just have it on your radar. So, you know, I do want to point out, and this is touches on some of my own work that's happening in Nick's lab right now. You can maybe automatically see that this could be really hard in some scenarios. So federated learning, you know, I think there's a lot of, in many ways, the act is an endorsement of federated learning and its privacy protecting qualities. But we know that you don't have access to the data, right? So for policing some of these qualities could be a little bit hard. We have a paper on arXiv that talks a little bit about this that we did with Tom. And it's not just federated learning, like we increasingly get our data sets or our models from closed sources, right? So Llama 3 is my latest example. Nobody knows what's in the training data for Llama 3, right? Maybe we know a little bit about it, but do we know that it meets those qualities, for example? Who knows? Probably not. So I think there's a lot of work. Preslav and I are working on a project about creating some artifacts that data and model originators can use to create, to share metadata about their training data and models that speaks to data quality and other compliance related issues more easily with downstream users. So these are just a couple of the thorny areas that I see with the data stuff. Another thorny area in my mind is human oversights. And a specific sub-requirement here is that human overseers have to be able to correctly interpret the outputs of the AI systems. So some issues that I immediately see here, as you may have heard, humans are actually pretty bad overseers of AI, due in part to various cognitive biases that we have both for and against automated decision-making. So we probably need, as researchers, to think through ways that we can support human overseers in the task of overseeing AI. I think there's a ton of work to be done there. Likewise, explainability, I think everyone would agree, is pretty much an unsolved problem. It has heavy trade-offs on the performance side, on the privacy and security side. We can't even seem to agree what defines explainability. So again, like I think there's like a lot of work to be done there to help folks stay compliant with that. And hopefully we'll get clear requirements around explainability from these standard setting entities. Accuracy, robustness, and cybersecurity. I have a couple bones to pick with this particular section of requirements. I'll be pretty brief here. I know this is a wordy slide, so sorry for that. But appropriate accuracy is a requirement in the Act. I think that's really ambiguous. You know, I know that even in taking the medical domain, for example, I think if you look at prognostic prediction versus diagnostic prediction, and even general practice versus specialty practice, what's acceptable accuracy varies dramatically. So it's tough to, you know, the standard setting entity will have a tough time of creating granular rules that really make sense for everybody. And even with those, we might still find ourselves struggling to figure out what's an acceptable level of accuracy for our machine learning model. With robustness, which is defined as the resilience to harmful or otherwise undesirable behavior, and cybersecurity, which is defined as resilience against attempts by unauthorized third parties to alter the use of the AI system's outputs or performance by exploiting system vulnerabilities. I just think of these both as pretty much unsolved problems, like you've probably seen all the work on jailbreak attacks and I think data poisoning and some other attacks are just very much still open problems, right? We haven't quite figured out cohesive defenses for them. So to require cybersecurity when some of these things haven't been solved is a kind of a thorny issue. So I'm keeping an eye on all this stuff. How am I doing on time, by the way?
I think you're doing good.
Okay. All right. So let's talk. Now, having talked about high-risk AI systems, which is the most heavily regulated category, let's talk about general-purpose AI. And again, you know, here's the definition. in the text of the law itself. An AI model that displays significant generality and is capable of completely performing a wide range of distinct tasks, regardless of the way the model is placed on the market, and that can be integrated into a variety of downstream systems or applications. I think the way to think about this, though, is it's foundational models, pretty much. Importantly, we talked a little bit about this kind of subcategory that's a little bit more regulated. General purpose AI with systematic risk. So that is defined as general purpose AI that has high impact capabilities evaluated on the basis of appropriate benchmarks. That sounds pretty ambiguous to me, right? I'm hoping that we'll get more clarity from these standard setting entities. They do have one clear threshold, though, which is actually kind of interesting. So you're presumed to meet that definition and to fall into this category if the computation you used for training exceeded 10 to the 25th floating point operations, flops. And just to kind of situate that where we are today, people think that GPT-4 was like a little bit over that. So I think what's happening here is they're trying to kind of skate to where the puck is going, and trying to set a figure that basically describes where the state of the art will be around the time this law goes into effect. I've heard people say that they think we're going to blow past this number so soon, and this will become like kind of table stakes, and this won't even be the cutting, or a better way to say it is that everyone's models will kind of meet this definition and fall into this category. So it's going to be kind of interesting to watch that, but that's where the line in the sand is today. If you fall into the baseline category, you just have to worry about creating a lot of documentation, registering your foundational model. If you fall into this GPAI with systematic risk category, a couple more requirements. You need to do an evaluation, like a state-of-the-art evaluation. You need to do some work to mitigate any risks. There's more reporting requirements if you see anything happening during monitoring, anything going wrong. You have to ensure the cybersecurity of your system. So just slightly more requirements if you fall into this bucket. I'm going to talk about a couple random issues, and then we'll kind of wrap things up and take some questions if anyone has them. Let me get a little bit more granular with the open source exception here. So if you're in the high risk AI systems category, there's no open source exception there. Likewise, if you're in this category that we just talked about, GPAI with systematic risk, there's no open source exception. The discrete open source exception exists if you are GPAI without systematic risk, okay? So if you're creating foundational models, you don't have reason to think that there's systematic risk. You'll get an exception from the rules of the Act if you open source that model. I'm not going to talk about them. There's a couple measures in the Act that are meant to deal with deep fakes. These involve letting people know that they're engaging with AI, doing watermarking or taking other measures to let folks know that they're looking at the outputs, like e.g. the images that were synthesized by AI. Just know that those are out there and check them out if they're relevant to you. A little bit more about the timeline. So this is mostly through the legislative process, and barring a surprise, most people I talk to think this will be finalized. I think the terminology there is entry into force this year, probably in the next couple months. There's a little bit of a delay, maybe 3 months, and then the rules about prohibited AI systems will be the first thing to go into effect. You will not be allowed to do those on the EU markets after that. Sometime in 2025, the rules around general purpose AI will go into effect. And then another year after that, these kind of more heavy regulations about high risk AI systems will go into effect. I think there's some flexibility here, so don't hold me to this, but I think the idea is maybe about 2 years from now, you could really see this regulation go into effect in a big way and start to impact the work you're doing for the EU market. So if you enjoyed my slides and you enjoyed this talk, I will be giving another talk on a completely different topic of productizing machine learning You can get RSP credit for it. That's next week, May 9th, 2 p.m. in the same room. So if you need to get some RSP credits and you're a Cambridge student, please come to that. Thank you. That's it.
Thank you so much, Bill, for this amazing talk and giving us so much insight into the EU AI Act. Are you ready for some questions?
Sure. Yeah, I'll do my very best for the question.
Okay, first of all, the room gets sort of the prime cut of the questions. Yes, at the back.
Thank you for your talk.
What's your name, by the way?
Yes.
Matthias. Good to see you. Thank you.
Yes. Is there still a requirement that you are responsible for any future release of whatever you release open source? I participated in a project like the European Commission, and they were talking about like for data, and I think for the model that they were responsible for any future use. That does not make any sense.
That's interesting. My interpretation is a little different. Though here's the way I think about it, and you know, I've spent 2.5 months looking really hard at this act, but there may be things that I'm missing.
Still defining this way, so early stages when we're trying to gather information. Sorry.
Yeah. Okay, got it. So let me just repeat the question. The question is sorry, I'm blanking on the question. Say it one more time.
Are the authors of models and data sets
Yep.
release them open
Yeah.
source for the community
Downstream.
responsible for the-
Okay, so if you produce an AI system or a model, do you have to worry about what happens downstream and how people use it? Okay, thank you. Thanks for reminding me. So my interpretation is like you need to check off all these boxes when you're developing it and before you release it. After you release it, there are other roles that come into play, like the role of the deployer. They do have obligations. The heaviest obligations are on the provider or the developer. I think if there's unexpected downstream uses, those people would be held accountable for those in their own way. My current, like, again, don't hold me to this analysis, is I think you as a developer like primarily have to worry about what you're putting out there into the world, right? And so if it's going to be misused downstream, you need to try to foresee those risks during the development. So that's baked into the requirements, right? Like foreseeing misuse and foreseeing unexpected outputs. You have to test for those things. You have to analyze those risks, mitigate those risks, document those risks. But I think after that, when it goes, you know, downstream, those other downstream users will have their own obligations. So that's my best take, but you know, we're all learning, and I might be missing some things. It's a great question. I really appreciate it. Of course, especially now where we're living in like the Hugging Face, you know, open ML kind of worlds. This is going to be happening a lot, like unexpected downstream use cases. So thank you for your question, Matthias. Really appreciate it.
Great. Any other questions? Yes, please.
Hi, thank you for the talk.
What's your name?
But
Okay, good to see you. Thank you.
I was going to ask, can you show the most prohibited case use case?
Yeah, absolutely.
Oh, sorry, Bill. It's gonna take a few moments.
Sorry.
Go for it.
There we go. You gotta watch all these things in reverse. Sorry about this, folks. We're getting there. We're almost there. There we are.
So, like, first question I want to ask is, like, probably some of this stuff is going on inside the social media companies' algorithms already. Is there any, like, auditing that is going to be done to those companies for this type of thing? Like, what does the enforcing procedures look like to investigate? Is there anything about that in here?
It's a great question. I haven't spent as much time looking at that. They definitely they've created new enforcement entities to look at this stuff. I don't know I don't know what it looks like in terms of like retroactively looking at things or that sort of stuff, but what I can definitely tell you is everyone's gonna have a little bit of time to get in shape, right? So I think part of the idea behind the 2-year lead time is that everyone who's putting stuff on the EU market has 2 years. If it's a high risk, sorry, I'm sorry, you're asking about prohibit. So let me roll that back a little bit. I apologize. Yeah, I think here people are gonna have to get their act together pretty quickly. I think there's a 3-month, maybe a 6-month delay. It's not long. I don't know for sure that anyone is engaging in this stuff right now. But yeah, the idea is like pretty quickly you're gonna have to pull this stuff out of market. I will say that people often do pull things out of market because they don't want to comply, because they want more time to comply. There's a pretty harsh biometrics law that came out in Illinois a while ago. I don't want to say harsh, but it's intense, and complying with it is intense. And a lot of people pulled out of the Illinois market temporarily or permanently in the wake of that to give themselves more time to comply with it, or because they just determined that compliance was not worth the expense. So here you could see that happen. People could pull out of the EU market for a little bit, or altogether. But I think the idea is like you definitely got to get your act together on this front pretty quickly. And it does make sense, by the way. Like most of these things are pretty noxious stuff, right? Like deceptive systems. Nobody wants that. So
based on your answer to the last question, so like these AGI type of general purpose AI type of models, they're treated as like completely like only a tool that these companies are developing, and their downstream use cases, maybe like doing something like this is just like as easy as like scanning all of the Twitter posts that someone has posted and then just like pasting it to the AGI model. Like even in those cases, how do you interpret stuff like that? Do you think that it's the general purpose AI category is separate and that would be a downstream case, for example?
I'm not quite sure I understand, but let me take a stab at it. Do you mean like if you scrape the open web, you're gonna maybe be getting terrible stuff?
Like if you want to do criminal profiling or like some social scoring, it may be as easy as to go to the Facebook posts of someone just taking all the posts that they have made, pasting it to this general purpose AI system and asking, okay, like what social score of that person be? And like the lines are very blurry. Like how do you interpret that type of use case?
Is the question mostly about like user behavior, like end user behavior? Or are you also meaning to capture with that question? Because that sounds like basically like at the prompt level or the prompt engineering level or something.
Yeah.
Okay. I think that's something that you have to foresee, and you have to assess that risk and like try to put in place mitigations. Users are not regulated by the act. You might be subject to other regulations like criminal laws, but they're not subject to the act. I think that being said, developers and deployers will probably have to think about what users are doing and make some kind of effort to de-risk those scenarios. I think that's the best answer I could probably give you. It's a good question. Thank you. Thank you for the good questions.
That sounded great, Bill. Well, thank you so much for telling us about this. A big round of applause for Bill. Great. So we are at the first intermission, the first and only intermission for this section. So we have a 20-minute break. Please help yourself to all of the wonderful pizza and drinks at the back, and talk to each other. Don't feel stressed. Just have a quick chat. In the meantime, we'll set up the next section, which is our tech demo. So stay around for that.
Because you were setting this as a formal thing.
Hello. Can you hear me?
Hello, Jan. How's it going? So we are currently live on YouTube, just so you know. People will hear us. I just need to arrange the screens a bit. That's okay.
Okay.
Okay, yeah. Say, I changed it to this.
Okay, Jan, you are on the big screen. Can you hear me?
Yes, I can.
I can't hear you though, so give me 2 seconds to figure this out, okay?
Sure.
Yeah, because I want to make a decision by
Yeah, I have one more question.
always.
Okay, we want to see what
Can you say something, please?
Hello, hello.
Hello. Okay, so let me put you through the big speaker to see how that goes.
All right.
Okay, try to say something now.
Hello.
Okay. Yeah. Say again.
Cool. Hello.
Okay, I can kind of hear you. I'm gonna bump the volume up, okay?
All right.
How come that they get classified as like nice?
Perfect.
Yeah, I just try to share my screen. Can you see it now?
Okay, just 1 second. I haven't set it up yet.
They're still trying to figure out what's not going to
Like future of life and students. I don't know. These type of students that are for you. There are benefits to
Perfect.
do you think that minor possibility or do you think that it's going to be a
Okay, Jan.
international. Private.
Cool.
Private integration was I think
Great.
one different story. Like the company is it's a great question. I haven't heard any.
Okay, Jan, can you hear me still?
Yes.
Okay, great. So, let me just put you on the big screen and we're gonna start.
Oh,
It's a great question. What do you
can you hear me clearly?
Like I think it's actually
You're on the screen. We're starting in a few seconds. Just let me introduce the topic.
we should have decided.
Okay, everyone.
Okay.
We are starting the second half of our talk. So, what we're actually going to be talking about now is more practical things. We're starting to talk about implementation and kind of brass tacks. So with us now, we have Jan, who is an engineer at Flower Labs, and he's been one of the people who developed this thing called Flower Tune. So we had a conversation in the beginning about federated learning and why federated learning is useful. We saw that federated learning allows us to have more data, access to more compute. One of the things that federated learning does really well, as well as it provides privacy. So what does that mean? Your data never leaves your device. Parameters that you create on your device leave your device, but those are not your data. So this kind of creates this level of privatization. And the most let's say, hot topic currently are large language models, and researchers are finding out that they're not particularly secure. Sometimes your data will leak. So we can use federated learning as a method to train large language models and fine-tune them while still keeping our data relatively safer than before. To achieve this, the researchers at Flower came up with this concept called Flower Tune, and Jan is going to talk us through it. So a big round of applause for Jan.
Thank you. Thank you, Prasad, and thank you, everyone. Yeah, so it's such an honor to be here and the first Google Develop meeting in Cambridge. So there's no camera towards the audience direction. So it's a pity I can't see your face, but I guess there's 1,000 people in the room, right? Okay, so let me start. So today I'm going to talk about the federated LLM fine-tuning with FlowerTune. But before that, let's talk about LLM fine-tuning first. So as we all know, LLMs has shown the remarkable effectiveness in a wide range of machine learning techniques across many domains, such as the general NLP task, the medical Q&A, the finance domain, the coding compilers, and so on. But how does a pre-trained LLM adapt to a particular task? So the thing we need here is fine-tuning the LLM on the data from the specific domain. With advanced development of LLMs, we have multiple choice of the pre-trained LLMs, such as the Gamma, the Llama, and GPT model, right? They have amazing model performance, but also on the other hand, it contains billions of parameters. So in this case, if we want to fine-tune them to a specific domain with all the parameters, it will indeed burn tons of GPU. Right? So of course, it's not eco-friendly, and also not much people can afford it. So is there any solution for that? A natural thought is that can we do the fine-tuning more efficiently instead of tuning the whole model? So yeah, here's I'm going to introduce one of the most popular parameter efficient fine-tuning method. It's called LoRa, low rank adaptation. Yeah, right. So which will introduce a low rank decomposition to modify the weights of a pre-existing network, allowing for the efficient fine-tuning. So how does it work exactly? So that's this example. So we have input vector, let's say with d dimensions, which will pass into the original pre-trained network with the weights of d times d dimensions. So instead of updating all the parameters in the large model, LoRa focuses on adapting only a small set of auxiliary parameters, which interact with the original model's weights through a low rank matrix. So here we have big A and B, where one of the dimensions of this matrix is R, and this R is way smaller than dimension D. And during fine-tuning, the original model is frozen, and only the metric A and B are trained. So this significantly reduces the number of trainable parameters, making the fine-tuning process faster and less resource intensive. And also, if it's need to use in a production, we can just explicitly compute the updated model weights, which equals to the original weights plus the product of B times A, and store the results, and then just performing the inference as usual. So this guarantees that we don't introduce any additional latency during the inference. And additionally, like swapping only the lower weights as opposed to all the parameters allows like cheaper and faster switching between the tasks, right? So that's amazing. We have LoRa technique for the LLM fine tuning, but we also have another concern from the data perspective. Most of current LLMs are trained on vast amount of publicly accessible data. However, despite the fact that more data typically lead to improved performance, some studies show that the supply of high-quality public data will run out within a few years. Additionally, if we use LLM fine-tuning for personalization, for example, on the user data, it will of course cause the privacy and security concern. And furthermore, there's often a need to build a more specified LLM that can integrate the domain-specific knowledge that's not available in the public dataset. So, for example, in the area of health, law, and also the finance. So, federated LLM fine-tuning offer the opportunity and solution to these concerns, which allows individuals or organizations to collaboratively improve a shared model without sharing their raw data. And it also provides opportunity for privacy protection, while also enabling the access to a range of pool of the protected data. So it addresses the issues such as the lack of public datasets. So to do federated LLM fine-tuning, now we have FlowerTune, so which makes the federated LLM fine-tuning very easy. So specifically, it allows LLM fine-tuning happening locally, and then only the LoRa-related parameters will send to the server for aggregation, which are typically less than 100 megabytes. So which also makes the message transmission very efficient as well. So how does FlowerTune work? So it basically integrates a bundle of techniques. First, it's including the Flower datasets, which is used to download, partition, and pre-process the training data. And also the easy change LLM adaptation with that easily change whatever model as a starting point to fine-tuning. So for example, the Gamma or other off-the-shelf models. And also we adopt the parameter efficient fine-tuning. So it's the LoRa technique as we mentioned before. And also we use quantization technique during the training for further speed up. In addition, with the Flower simulation engine, we are able to efficiently make use of the computer resource to do FL simulation. So all of them come together to make LLM federated fine-tuning, which can be done just a single GPU. All right, so both can integrate with few Google techniques. That means we train the Gamma model with JAX. My colleague Teresa will show you an amazing demo later. All right, so that's pretty much what I want to share today. So thank you for your attention, and feel free to join Flower's panels for the further discussion about federated topics. Thank you.
Great, thank you so much, Jan. Big round of applause. Cool. Any questions? Okay, well, Lorenzo, do you have a question or? No? Okay. Jan, so no questions. Thank you so much for the very clear explanation. I'm going to take it from here and dive into the technical demo. So thank you so much for coming over. Another round of applause for Jan.
Thank you so much.
Cheers. Thanks so much, Jan.
Yes.
Okay, everyone. So we have officially finished with the talks, and now we're going to go into a kind of technical tutorial, technical demo thing. I'll be doing this, and I'll try to make it super interactive. So I'll go through all of the code, and feel free to stop me or ask me questions about what's going on. So let me just share the proper thing on the projector so that we can start looking at the right things. So I just need to also fix the stream very briefly. Okay, we're here. So we can see our code, and people online can see us as well. Great. And I just need to check one final thing with the stream before we go. So bear with me for a few moments here. Just need to do some magic. Okay. And people online. Okay, cool. So they should be fine. Great. So let's begin. I will make this a bit larger so that people can see, and I'll hide this part. Great. So Jan gave a talk on Flower Tune, and he talked about LoRa, and he talked about sharing LoRa parameters. I'm kind of gonna say what he said again, just in a very, very condensed way, to kind of tie it in with what I'm going to show you code-wise. LoRa, you basically attach some extra weights to a big model, LLM, and then you fine-tune those weights rather than the big LLM. This is really good because computationally it's very fast. It's even more secure than before. Well, I won't get into details why that's the case, but it is. And it's easier when we apply federated learning because the number of parameters we have to transmit is super tiny compared to the big LLM. So Jan spoke briefly on using JAX and using Gemma. Those are two Google technologies that I would like to introduce to you. So probably most of you know what JAX is. Maybe you've heard it. It's been around for a while. It's still in development, but it's a very kind of novel machine learning framework. And probably a lot of you know about Gemma's brother, Gemini, which is Google's kind of ChatGPT alternative. Gemma is the open source version of that. So what I want to show you now is a few things. There's a few questions, I guess. First of all, why is Gemma special? And second of all, why is JAX special? So for JAX, I would like to show you a few experiments. And what I want to tell you is that JAX is optimized for speed. It's optimized to run close to hardware so that it can go quicker than anything else. This is very important because, as Nick said in the first talk, compute is limited. It's very expensive to have compute. So if we can optimize our compute, we can optimize what we do. On federated devices, it's even more important because if it's a constrained device, having an optimized system there really helps us. Great. So JAX aims to kind of or answer these questions of optimization by running close to hardware. Now, JAX itself is a NumPy alternative. It can also work as a PyTorch alternative, and we'll talk about this a bit later. But now I just want to kind of gauge the differences between JAX and NumPy, just to show you where JAX shines. So in this tutorial, what I'm going to do first is this is a regular notebook, and I'm absolutely sure that most of you have seen this before. If you haven't, this is a notebook. This is a place where you can run individual pieces of code, and each piece, does a thing. The language we're using here is Python, so I'm going to import 3 key libraries. First off is NumPy. NumPy is kind of the standard when it comes to numerical processing. Then we have JAX NumPy, which is kind of JAX's implementation of all NumPy functions. And finally, we have the JAX JIT, which is our just-in-time compiler. The thing that looks at kind of the computational graph, compiles it down as it runs, and optimizes it for the hardware that's available. And to show you how this works, what I'll do is I have created a little function, fn, and this function, as you can see, it just adds three numbers together. That's x, x squared, and x cubed. So it's pretty simple. And then I'll create a relatively large NumPy matrix, and I will pass this matrix through this function, and I'm going to time it, and I'm going to see how long it takes to execute. So that's what's going to happen now. First import, and then I'm going to run the NumPy version of this right now. So this little flag here is called timeIt. It times the execution of a function, I think a few thousand times, and then prints a little statistic on how quickly this function executed. So you can see here, the NumPy version executes on average in 1.24 milliseconds. So NumPy takes 1.2 milliseconds to do however many computational cycles it was supposed to do. Great. How do you think JAX is going to perform here? Any ideas? I argue that JAX is going to destroy NumPy completely, primarily because of this, the JIT. So let's see, let's run it. So as it runs, JAX is examining what kind of calls the CPU is doing, and it's optimizing for those and compiling down. And here you can see we have 79 microseconds on average. So that's a lot quicker. So JAX versus NumPy, there's no contest. Use JAX. Great, but we're here to do ML. We're here to do machine learning. So how would this work with PyTorch? So let's see here. We have a PyTorch example. And for this PyTorch example, I've decided to kind of give you a few different levels of complexity here. What does that mean? I have a few functions, and assume that those functions are layers in a neural network, right? So we have layer 1, layer 2, layer 3, and then we have the final layer that does everything. I've tried to make them as nasty as I could, right? We have something to the power of 2, we have that thing to the power of 2 times itself, we have then that thing to the power of 3, it's just like, wow, if you want to take the derivative of this, it's gonna take you a while, right? So how quickly will now JAX be able to decipher all of this information and get us a gradient? Let's find out. Just like before, we import Torch, we import JAX. It's gonna take a while. Both are big libraries. I'm gonna commit these functions into memory. I'm going to add them to the JIT, and then I'm going to ask JAX to calculate the gradient of them 1,000 times, and time it's going to tell me how much time. And let's see. So now we're running this, and JAX is doing all its magic. It's compiling everything down, and you can see it took JAX 1 millisecond on average to calculate all of these gradients, right? Amazing stuff. Now we have the competitor, PyTorch. Now, PyTorch's gradients work a bit different than JAX. JAX is a purely functional language. So I've redone the same formula, just in a single function, so timeIt can capture it properly. So we'll run this, and we'll see that NumPy's version of this takes only 200 microseconds. So in fact, NumPy is a lot quicker than JAX, right? So what gives? Like, JAX is supposed to be optimizing, it's supposed to be compiling everything down to the JIT, with the JIT. So there's some problem here. I think we should investigate this a bit further. And the way to do this is we'll look at sort of a different way of comparing these frameworks. So I propose to you that JAX's JIT and its ability to optimize don't really shine when we're optimizing something small. In this example, the function that we're looking at here is getting the gradient of this thing, which I said was really, nasty. But from a computational graph perspective, this isn't really a big deal. It's just one thing, the other thing, the next thing. It's not really difficult. So what if we give it something really difficult? And here I have a little function that I've created. And this function basically creates a list of consecutive numbers where each element is 1 plus the previous element. So by the time you get to the very final element, you have a computational graph that depends on every element prior in the list. So you have a very big computational graph. Then you take all of these things, you sum them together, and this is your function. So I'll execute this function just to put it into memory. And just as a little kind of sanity check, I'll hide this, I'll show this later. Just as a little sanity check, I'm gonna run this, see how it goes. So as you can see, the sum of the first 100 numbers is 4,950. So we know this function works correctly. So now let's see how long it will take Jax to get the gradient of this function for the first 10 numbers. We run it, and we'll see that it will take Jax roughly, let's see, 100 milliseconds. Great. What happens if we give it 100 numbers? It's gonna go again, it's gonna run, let's see how many loops. And again, roughly 100 milliseconds. Okay, let's give it 1,000 numbers, see what happens with 1,000 numbers. It still takes roughly, 100 milliseconds. Let's see what PyTorch will do in a similar environment. So we import PyTorch, we define the same function as before, and just as a sanity check, we'll print the sum of the first 100 numbers. It's the same as before. Great. We define our gradient function, just like before, and now we go with timings. So let's see. Timing for 10. Timing for 10 is going to be 500 microseconds. So that is roughly 200 times quicker than Jax. So Jax is obviously underperforming here. What if we do it for 100? If we do it for 100, we see that it's 5 milliseconds, still beats Jax. So there's absolutely no contest. What if we do it for 1,000? Okay, this is twice as fast as Jax. And now we'll do it for 10,000. Okay, now it's around 600 milliseconds. Now, I've done these experiments before to get the numbers, so I'll draw a little plot for you guys just to show you what happened in case it wasn't that clear. Regardless of the size of the array I gave, Jax always gave us a constant execution time. Whereas PyTorch, its execution time depended on the size of the input. This means that Jax computational complexity here is constant. It's big O of 1, which means that it's really, really good at scaling. Because it's good at scaling, its initial performance on small computational graphs is worse than PyTorch. But when you actually start applying this to very big models, computationally, Jax beats PyTorch by a lot. And so this doesn't help you with RAM or with memory, with VRAM, but it helps you with computational cost. And if we compare this to NumPy functions, which PyTorch will inevitably use when you start averaging parameters or extracting data, Jax again beats NumPy there as well. So in general, using Jax versus NumPy and PyTorch is the better way to do it, especially for big models. So this is kind of the reasoning why we're gonna be looking into Jax and why we're gonna be looking into Gemma. So Gemma itself is a very, very big model. And the thing that makes Gemma special is the fact that its vocabulary size is roughly twice of all other large language models. So recently, Llama 3 came out, and it has a vocabulary size of 100K, which is great. But Gemma has a vocabulary size of 256K. So even though the model came out last year roughly, it still has cutting edge vocabulary size. And that makes Gemma very good computationally, like in the sense that the larger your vocabulary size is, the smaller your tokenized input, and the smaller your tokenized input is, the less compute you spend on running this. So in terms of computational power, Gemma is more effective. Great. So these are the things. I wanted to show you how the computational graphs looked for Jack, so you can see kind of the difference in what it's trying to do. Are you guys interested in that, or we can skip and start playing with Gemma directly? Okay, who wants to see a computational graph of a very complicated function? Okay, who wants to go and play with Gemma directly? Okay, we'll go play with Gemma, and if there's time at the end, I'll show you some computational graphs. Cool. Okay, so now we get into Gemma. So as I said, Gemma is a large language model that has a huge vocabulary size. And in order to run it, we need a GPU. There's no way of getting past the GPU needs. So I'm gonna run this to just get some information, and I'm gonna load the smallest Gemma model possible, which is the Gemma 2 billion model. I'm gonna play it here, and it's gonna start downloading from Kaggle, and it's gonna give us a little summary of what the model is. Now, in the meantime, I'm gonna check the YouTube very quickly just to see if people are saying anything. No, perfect. So everything is fine. And Gemma loaded. Okay, so we have Gemma. We can see its tokenizer, 256,000. That's great. And we can see that it has 2.5 billion parameters, which equates to roughly 9.34 gigabytes. So this is our Gemma model. What can Gemma do? Well, Gemma can do anything any large language model can do. It can chat, it can generate stuff. So I'm just gonna go and ask it a very easy question. Everyone knows this, right? So we'll just run it and we'll see what Gemma thinks.
And you need the text, Peter.
Of course. So according to Gemma, the meaning of life, the question is one of the most important questions in the world. It's the question that has been asked by philosophers, theologians, and scientists. It is the question that has been asked by people who are looking for answers to their own lives. Sadly, we ran out of length, so that's all we're gonna get. Maybe if I increase the token count, we'll get some more answers, but this is what Gemma gives us for now. Gemma can also answer things in batches. So I can give it 2 questions at the same time, and we can see what Gemma says. So we can ask it another very simple question, obviously. How does the brain work, in addition to what's the meaning of life? And we'll see what Gemma thinks. Okay, so we have it here. We see that the meaning of life answer is exactly the same as before. And we see that how does the brain work is probably a good answer. I don't know. If anyone knows biology, they can say. So it can do that. And it can also do template answers. So template answers are the thing that ChatGPT uses, for example. It's a way for you to give context to the LLM and to get a response from it. So I'm not going to generate this as just some information. Gemma can use different sampling techniques, which any other LLM can do. And the reason for that is, I'll run the previous one just to show you. Sometimes they break down. LLMs don't necessarily work well if you use a greedy approach to sampling. So if I asked it, what should I do on a trip to Europe? It says, well, you should go, just do it, right? It doesn't say what to do, it just says do it. So we can use a different sampling technique and in the hopes that we get better results. And that's what I'll show you here. So now in the whole framework, I have compiled Gemma with the top K sampler, which is a simple beam search. And that goes through and shows us, okay, look, what should I do in Europe? It says it's easy, you just need to follow these steps. Book your trip with a travel agency, choose a country in the city, choose your hotel and your flight. Pretty straightforward, right? So we see that top K sampling improved the response quite a lot. Great. I can ask it what the meaning of life is again, but believe me, the answer is much the same. However, there is a situation where large language models fail. What does that mean? They don't fail in the sense that they don't work anymore. They fail in the sense that their information is limited. They're trained on general purpose datasets that talk about all sorts of things. But if you ask them something very specific, they don't really know how to answer, or they give you an answer that's insufficient. So I'll give you an example here. This is a sample which is called Explain Like I'm 5, and there it says explain the process of photosynthesis in a way that a child could understand. So if I run this, we'll see what Gemma thinks a child can understand. And obviously, we know that this doesn't work particularly well simply because children can't compile LaTeX code. So yeah, we see that this answer is actually not the right one. It starts talking about some reaction. It starts talking about 40-liter containers. It doesn't talk about photosynthesis. Great. So how can we fix this? How can we make Gemma or any other LLM work better? Well, what we do is we fine-tune it. And how do we fine-tune it? Well, we fine-tune it using Flower Tune. And I'm going to show you now two things. First, I'm going to show you just centralized fine-tuning. And later, I'm going to show you how to implement all of this into a federated setting. So centralized fine-tuning is made very simple with Gemma and its API. You enable LoRa, and you see the nice LoRa parameters here that are around 5 megabytes. So that's the only parameters that we'll fine-tune. We download some of the data, and just to keep this nice and quick, I'll only leave 1,000 data samples. That doesn't matter. We give it an optimizer, we give it some weight decay, compile the model, and fit the data. So pretty straightforward. I run this, Gemma does all of its things, and it will show us some results. Now, when you see this working, you have to think a few things. You have to think, wow, like this is super easy, it's super nice. But you also have to think, where is this data coming from? Where is this fine-tuned data set coming from? Like, how did I get it? And this is where federated learning is really useful. If you want to take Gemma and you want to apply it to, let's say, a medical data set, a hospital might not want to give you its data, right? It's super private. Or let's say you want to use this in insurance. An insurance company will never give you its data. So how can you leverage machine learning and leverage some of the information from an organization like a hospital or like an insurance company? Additionally, if you want to guarantee that maybe your private data that you have access to doesn't get transmitted and endangered, what you can do is use federated learning. So I'm going to stop this now. You see that here it's training, and we'll go into the Flower fine-tune example. And I'll show you how simple it is to actually use Flower. So Flower has a few specific requirements. They are the creation of a client and the creation of a server. So as we know, federated learning is the idea of having an aggregation of clients together talking with one server. You need to program that client and the server. There's a few standard functions that you need to follow, and those are shown on Flower's website, on their GitHub. And later on, I will also share this code with all of the participants here, so you guys can kind of look through this. But essentially, your federated client has a way to share parameters, has a fit function, and in addition to that, has a way to create a model. That's pretty simple. The server itself has a way to get a configuration, which is to get the current round, and a way to average some results for us. So as you can see, yes, please.
I have a question about the process of like this federated learning. Are they sending like gradient updates? Are they updating the models, copying themselves, and then you merge those? Like, I'm confused about that process. There was something about low rank matrices, but I feel like I don't fully get it. Can you elaborate?
Of course, absolutely. So just for the people online, question is, how does federated learning work in this case? So, okay, what's the idea of federated learning? You have a bunch of models. We can call those models clients or devices. There's model parameters living somewhere, and they have access to their own local data, and they do their own training. So your smartphone, its keyboard is training from your input. All the people here, their keyboards are personalized to themselves, and they have model parameters. So now the question is, how can all of your phones learn together without sending your text messages to everyone in this room, right? So what happens is we extract the model parameters from your machine learning model, and we average them with everyone else's. So on average, we get a really good model, and we send that model back to every client.
It's like it's the same model, same number of parameters, and each parameter is the average of everyone that has.
Correct. So that's the simplest way of doing federated learning, right? There's more complex ways that we won't get into. How does this play with LoRa? So you have a big LLM that's 2.5 billion parameters. We don't want to transmit 2.5 billion parameters. That's too much. LoRa attaches like an adapter to the LLM. That's very small. We saw it's only 5 megabytes. And we only train those 5 megabytes and then transmit only those 5 megabytes. So that plays really well with federated learning because you minimize transmission cost because model parameters are smaller than raw data. And additionally, we minimize the size of the model we're transmitting. So it's a double minimization kind of benefit.
Is it a subset of the model parameters, or do you compress them?
What do you mean?
Like, how do you, are you only sending a subset of the model parameters? Or how do you make updates without, like, knowing all?
So in the LoRa case, the base model is the same across everyone else. So you download it once, and that's constant between all clients. And then the LoRa parameters are the ones that are being averaged, right? So that's basically the whole situation. Does that answer your question?
Yeah.
Great. Thank you so much for the question. So yeah, we have a server, we have a client, and now we can go and see how this works. We first import, I need to select the kernel. Sorry for this. So first we need to run our libraries. I just realized something, by the way, while I was talking. There is a small chance that I will run out of memory because I've already loaded this model once. So if it gives you some error, that's probably a memory error. We need to load a configuration, which is here, and that's just standard kind of Python ways of getting configurations. And then we're going to use kind of the first place where Flower comes into is these federated data sets. There's a whole thing about getting federated data, but this is basically the easiest way to do it. You give it any Hugging Face data string, it will download it for you, partition it into separate partitions, and break it up into each client. So from that, we get our federated data set. Then we create our client app, and we basically give it one of these client functions that we have defined in the client script. So here, there is a function that takes all of this information, conditions it based on the ID of the user, so the CID, and then from there, it returns our Flower client. Okay, so we have that, and let's just give it a quick run. So now we have our client app instantiated, and then we create our server. So the server takes a few things. It takes a strategy and it takes a server config. Server config is super simple. We just give it the number of rounds. The strategy is what the question was related to before. Federated averaging is this idea of averaging everyone's parameters. And this is the fedav strategy. There's millions of other strategies, but this is kind of the simplest one. And it's implemented in Flower, so you can directly use it. You don't need to implement it from scratch. You can set all of the important parameters, like the number of clients, the fraction of clients that we use for fitting, how many of them we need to evaluate, so on and so forth. So I'm going to run this as well. And then finally, you have FL simulation, run simulation. So in order to do proper federated learning, ideally you would have access to thousands of devices, but companies like Samsung and Apple, they don't really like giving you this data, right? We've tried, they don't do it. So what we can do is we can simulate all the devices we want. And Flower provides us this capability. So with Flower, you can both simulate your federated model and then also deploy it, because Flower has a deployment side as well. It can control clients just as well as it can control simulated clients. So with this, you just click run, and it starts running. So it starts creating a simulation framework using Ray. it starts loading the model and it starts doing federated learning. So that's basically it. That's how you fine tune an LLM using Flower Tune. And with that, you can alleviate some of the issues in large language models like Gemma, similar to the ones I showed you earlier. Thank you so much for your attention. Any questions? Yes, please.
Would this setting also make sense if you don't want to, like, it's okay that you have all of the data, but you only want distributed training? Can I use the same library? Like, I don't need the federated learning necessarily.
Okay.
But can I use the same library to just distribute compute?
You can, indeed you can. So there's a paper from Google Research actually that shows that federated learning is the best way to do data transfer within even a device itself. So if you want to distribute the learning and not federate it in the sense where you have separate devices, you can still federate it on a single device. And that's the most effective way to achieve this. It's still federated learning. So you can adapt Flower and adapt the strategy to do that. Okay, second question over there. Yes, Luca?
So earlier on you were talking about how DAX is designed for the optimizations, at runtime, especially with like the JIT and everything. So I was just curious, like, is it designed to be deployed like kind of on multiple devices and resource constrained devices, or is it like kind of covering like the whole device ecosystem, like across the board, like something like PyTorch is trying to do?
So it's trying to cover the whole ecosystem. It's not particularly optimized. It's optimized to run close to the hardware, right? So the issue with, let's say, resource constrained devices is that you need to get the whole thing on there first for the JIT to do its thing. There might be workarounds for this in a sense where you could simulate or extract the compiled model from JAX and then run it on resource constrained devices directly. That's probably possible. But JAX is trying to be a computational backend. So you can see that through this tutorial, there's been I'll actually show you. There has been a lot of keras mentioned in the code here. So I'll show you at the very beginning. This is a keras NLP model. It just uses JAX as a backend. So JAX is designed to be the engine of ML. Thanks so much for the question. Any other questions? Tom?
So do you know what's the technical rationale or like the magic behind the scenes, like how come is JAX so much faster?
So good question. It's purely functional and stateless, and I think that's one of the things that helps the JIT compiler do its thing. It's a different paradigm in programming, and that works better. Apparently, I don't know why, but it works better in computational stuff. So in the computational context, and PyTorch is optimized to kind of run everywhere and to be very intuitive and similar to how Python is written, but that comes with some bottlenecks. JAX kind of throws all of this out and is purely done with performance in mind.
And is it like does it use hardware acceleration or anything fancy?
It can if you want to. JAX is the best way to run to run ML on TPUs. Cool. Yeah, I'm listening.
I was surprised at how impactful the choices sampler was. How do people choose the right sampler? Is there the sampling method? Are those things publicly benchmarked? Like how do you go about navigating that decision?
So, okay, the choice of sampler. So sampler basically means if you have a big selection of choices, you pick one and then you have another big selection of choices and you keep picking and you'll get sort of a decision tree. And you can do that for every decision and you'll get a very big decision tree. And that takes a lot of time to do. So what your consideration there is, how many branches do I want to explore and how deep do I want to explore them before making a concrete choice? So sampling, you can do, as I said, top K sampling, which takes the top five most probable choices now and goes, let's say, one level deep. You can take bottom K sampling. You can go more than 5 levels deep. You can do whatever. It's just how much compute you want to spend on this. And usually the thing I showed you first is greedy search, which usually works the worst out of all of them. You take the next most likely token, which leaves you in this kind of loop of perpetual repeating messages. But it takes no compute. So on your phone, when you have autocomplete on your keyboard, most likely it's using the greedy approach. So if you click on the next suggestion of your keyboard, it's going to quickly start repeating itself. And that's what I showed you earlier when it started saying, take a trip to Europe, take a trip to Europe, so on and so forth. So that's it. Thanks so much for the question. Any other questions? No? Okay, cool. Well, thank you everyone for coming. This was the first Google developer meeting of in Cambridge. So yeah, thank you for being here. A round of applause for everyone. If you guys want to stay around and chat and hang out, please feel free to do that. If you want to leave, you're free to leave. Then no one's holding you back. To those who are interested, I'm going to show you some computational graphs now. Everyone else? Yeah. Really well. Okay.
I don't want to know how they got to it. I just want to know that they're running.